Okay, great. Hello, everyone. Welcome to another seminar. Teaching as a guest today. Today's speaker is going to be Ilse. She's going to talk about extending the natural history model for prostate cancer using data from screening trial. Ilse, the stage is yours.
Thank you. Right. So thank you everyone for coming. As Evan said, I'm going to be talking about a model for the natural history for prostate cancer. This is joint work with my supervisors, Arda van der Hout and Nora Pashayan. We can see the room. Do we need that?
Yeah.
Okay. Right. So a little bit of the structure. So first I'm going to talk about the motivation of the research. Then I'm going to introduce the multi-state survival model. And I'm going to be talking about two different data sets and two different applications. So the first one is going to be about liver cirrhosis. That's a randomized trial. And the second one is going to be about prostate cancer. So medical research often involves studying signs in which biomarkers are measured repeatedly over time. So what is a biomarker? A biomarker is an objective medical sign that is used to measure disease progression or the presence of a disease. So a biomarker can be a blood test, can be also a scan, an ultrasound that can tell the clinician that there is a progression of the disease. So if it's a blood test, we're going to have the same measurement repeatedly over time. And what happens commonly is that if we think about the classical survival model, we can think about it in a two-stage model. So first, we define the starting time, and then we follow up until a certain amount of years, and then we see if the patient died or not. So it's just a two-stage survival model. So we can describe this process in two different ways. So we can look at the probability density function, or we can look at its hazard function. So what's the instantaneous rate for moving from one state to another? If we assume this hazard is constant, for example, we will be defining an exponential model. But it is often the case that we want to account for patient characteristics or anything that might be influencing the survival of the patient. And a common way to do it is just using a Cox regression model. With a Cox regression model, we can explore the effect of a longitudinal biomarker, but we cannot use it for prediction because we're not modeling this process. So what can we do? So if we have, for example, a biomarker that we can just classify it as a discrete biomarker, 0, 1, present or absent, we can then extend the two-stage model that we just described and have two living states and then the transition to that. So we can model as well the hazards and then the probability from transition from one state to another. And that would be a multi-state model, right? So basically, if we can adequately discretize this biomarker, we can define a set of living states, and then we can define a multi-state model. So more formally, what's a multi-state model or how we define it? A multi-state survival model can be defined as a model for a stochastic process. And what is a stochastic process? A stochastic process is a set of random variables representing the evolution of the process over time. So we can either look at discrete time or continuous time. So from now on, all the models are specifically in continuous time processes. Right, so we're talking about stochastic processes. We need to define as well the probability transition matrix. So a multi-state survival model is going to be a continuous time stochastic process on a finite state space. So in this case, it's going to be indexed from 1 to D, where D stands for death. And then we're going to have the probability transition matrix. So that's going to be matrix dimension P times D, the number of finite states. And each entry is going to be the probability of transition from one state to another in the given interval of time. So if we look at these transition probabilities, we can see that these transition probabilities can be a function of time t. And how we compute the transition probabilities is the next question. So that could be done by using the transition hazards. So we can think about the transition hazard as the instantaneous rate from moving from one state to another. And can people listen to this? Because no, I just got an alert that I'm on. Oh, that's okay. Just gonna close that. Right. So we're talking about the probability transition matrix that can be derived by the transition hazards. So we define the transition hazard. We're as well gonna have as many transition hazards as states or as possible transitions. Sorry. And then we're gonna have the generator matrix. So the generator matrix is gonna help us. Sorry, I'm just getting warnings, but it's fine. Compute the probability transition matrix. So this is an important aspect of the multi-state survival model. So with the generator matrix, we can compute the probability transition matrix, and how we do it is through the matrix exponential. So what does that mean? This equation basically. So we define an interval of time, and then we have now the link between the generator matrix and the probability transition matrix. There are different ways to compute this matrix, and one common way to do it is using eigen decomposition. Right. So now we think about the probability transition matrix and the slide that I had before. This can get quite complicated. So if we have time-dependent probability transitions, we get time-dependent homography differential equations, and it's not very straightforward if you want to get the explicit solutions. Or there's also been proposed to have like some sort of transformation with time. But another way to do it is just assuming piecewise constant intensity. So what that means is that you assume that it's constant within an interval of time. And this interval of time, if you are in a clinical setup, can be the time that the patient comes to the clinic. So the follow-up. Right, so now we have defined the transition probability matrix, the hazards, and more specifically, we can define the transition hazard as a log linear regression. So now we can add any sort of covariates here as well. So how does the likelihood look? So we have an observed trajectory for an individual I. So we have the joint probability of that observed trajectory conditional to the first state, the parameter vector and the covariates, and that could be decomposed as multiplication of conditional probability. So basically what we saw 3 slides before. Depending on the transition we have in the last element, this multiplication gets modified. So if we have a right sensor observation or we have an exact time transition, that would be a transition to death, for example. Or if we have an interval sensor transition. And by interval sensor, I mean you don't really know exactly the time the transition happened. You just know the interval of time that happened. So that would be the likelihood contribution for an individual. And then if we sum through all the individuals and all the observed states for individuals, we get the full likelihood. Right. Okay. So this is a brief summary of the first 10 slides that I talked about. So we have the probability transition matrix. How we compute that, we define the hazard transitions. Therefore, we define the generator matrix that's indexed with the H. And that way we get the probability transition matrix for a given interval of time. And then if we have that, then we can have all the transition probabilities and we can have the likelihood contributions and we can build our likelihood function, right? There are different ways to maximize this likelihood and we can use a general purpose optimizer to do so. Okay, so now we're gonna start with the first example. So for the first data set, this is a clinical trial for liver cirrhosis data. And the main aim was to do treatment effect comparison. So basically we have a control group that is given placebo and an intervention group that is given a treatment and they follow up for time and then they see if there was an effect on survival. So in this case, we have a longitudinal biomarker. So we go back to the first slide. We define what a biomarker is. So it's basically a measurement that the doctors are going to use to see if there's progression of the disease. So in this case, we have something that is called the proton-mean index. That's a blood test. So the patients are coming back every 3 months for the first year, having this test, and then the clinicians are testing if there's this progression or not, giving the results of this test. So we have a longitudinal variable, and we have the survival of the patient. So something else that is important of this process is the normal range. So when the doctor looks at the results, if this biomarker is between 70% or 100, they're like, okay, everything's fine, just go home, come back in 3 months. If it's not, there might be or not an intervention. So if we recall the first slide, we define we mentioned that the multi-state model can be built if we can discretize this biomarker. So we started with a very simple example where we have a discrete longitudinal variable where we can just have 0 and 1, and we extended the 2-state classical survival into a 3-state multi-state model, depending on the result of this biomarker. So basically, we're borrowing the same idea, but now our biomarker is defining the real values. So what happens if we have the real values? Exactly the same. We can just discretize it. We can define a finite number of living states, and then we can model the hazards, and then we can see the survival probability. So that's what I did. So I had a biomarker, a longitudinal variable, defining the reals, and then I discretized it into 8 different living states. In that way, you can allow for the patient to move within these living states. And why is that important? Because these biomarkers can fluctuate, so they can get abnormal test results and they can go back to normal again. So you need to account for that fluctuation, and you can model that, which is allowing for the transition. And yeah, so that's how the first step, we define the multi-state model, we define the process, and now we need to define the transition hazards. So as I mentioned before, it's not only looking at the biomarker in itself, but looking at what is considered normal or abnormal. So what could be affecting the survival of the patient, or what information can we get out of this biomarker? So we mentioned that the normal ranges were between 70% and 100. So basically what we would expect is to have a different hazard from transitioning from a normal range of this biomarker than from a lower or upper bound of this biomarker. Why? Because if it's lower, then that indicates that there's some hepatic failure, or if it's very high, same story. So we would expect this hazard to be higher. Right. So how can we do that? So you would think, okay, maybe we can just define different parameters for all the hazards and then model 8 times a very, very large multi-state model. But that's a problem, because within multi-state model, as I mentioned before, we have the exponential matrix, and it's not very straightforward how we do it. And then we face convergence issues and identifiability problems. So that's an issue that you can face when you are fixing a multi-state model. So a way that we thought we could save this problem and still account for this symmetry within the hazard is by defining a new variable. So we defined DVR as the distance between the numerical value of the living state and 4.5. So why are we doing this? So if we think again, what is normal? It's 70% to 100. So basically, the closer you are to these two states, the better your survival should look. And as you go closer to the boundaries of the process or of the model, then you might have different behavior of the survival, right? So this was, and we defined that variable, and then we just added as a predictor in our hazard function. And in that way, we are kind of accounting for this symmetry within the hazards and this different behavior within the hazards, but in a less expensive, less computational expensive way. Also, so we have that variable, dr, and then we have the treatment effect, and then we have time with some splines. So I don't know if you are familiarized with splines. So basically what splines do is just give us a bit more flexibility with the form of the hazard. Before I go to the next slide, is there any questions with the equation? There's also hazards model for the transitions within the living state, but just wanted to focus on this one for now. Are there any questions with this slide? No, it's fine. Okay, so if we, how do you decide how to discretize the biomarker? Yes, that's a good question, Bunny. So basically, I started with uniform discretization. So this biomarker goes from 0 to 200. And I just thought, okay, let's do 10 states uniformly. And then I joined together the last 2 states of the process because there weren't really enough information in that boundary. And then yes, and then I just tried to fit the model and compare it, but obviously this is also a decision that has to be made together with clinical advice, if it makes sense and what is interesting to see from the process. And you can also like compare different numbers of living states that you defined and see what works best. There's another question. What are the models for the living transitions? So for the living transitions, we have the treatment effect as well and time. So we constrain all the forward transitions to be the same and all the backward transitions to be the same in order to fit the model. I hope that is okay. But yeah, thank you for asking. And then, so that was one way. And then we also thought, right, so if we're including this distance variable, can we just also include the numerical value of the living state as a predictor? And how would that look? Would it make it better or not? And we did it. And then, similar to the previous slide, we also included splines. And this is just, again, to give a little bit more of flexibility of the forms that we're modeling. And yes, so this is the second model, just using the living state as a predictor. Then I fitted different models and then compared them based on the AIC. And choose the one that has the lowest AIC. So in this case, this model, the one that is not highlighted in blue, has a lower AIC, but we didn't have access to the standard errors, and that's also another thing that could happen with multi-state models. If you face a saddle point or you're close to a boundary of the parameter space, you might not have access to a standard error, so you cannot really do prediction. So we chose this model that penalizes clients, and this is just to talk about what is penalizes clients. So basically, if you do B splines, you face the question that how many basis splines do you have to choose? And one way to go around it is just by penalizing. And what the penalization does is it penalizes the adjacent coefficients of the B splines, enforcing them not to be too different from each other and enforcing smoothness. So this slide is just to say that how the penalization and the degrees of freedoms of the model varies depending on the penalization. And that's because if you have a small penalization, then you're allowing for more flexibility within your curve. Whereas if you have a high penalization, then it looks more like a straight line. So the degrees of freedom vary depending on the penalization as well. Right. So coming back to this slide, we're just gonna focus on this model, and I'm gonna show you the prediction and a tool that we use to see the goodness of fit of the model. So if we talk about goodness of fit, we can just compare the model-based estimated survival to the Kaplan-Meier curves and see how it performs. It is important to mention that this is only assessing the survival part of the model. So it's not a strict tool to be used for goodness of fit, but it can tell it's informative though. So we have the blue curve that is plotted here. That would be the median of the model-based estimated survivals. And then we have the Kaplan-Meier curve and the confidence interval. And we can see that the model performs quite well. So we have the median falling within the 95% confidence intervals of the Kaplan-Meier curve. And then, I don't know if you've heard, another framework that is quite popular when you have a longitudinal biomarker and a survival or a time to event outcome is the joint models. And roughly speaking, what is a joint model? A joint model is a linear mixed effect model that models the longitudinal part of the model with random effects, and then the survival outcome as a Cox model. And yeah, so we compared our model to the joint model using based on the prediction of the survival. So we did 200 realizations of the predicted survival. And then for the joint model approach, we have the standard errors that are based on the Monte Carlo scheme, where the target distribution is the Bayesian representation of the joint models. And then for the multi-state model, we have the standard errors being computed by using the multivariate delta method. So what we are seeing here is the predicted survival for a patient that has biomarker level, a low biomarker level. And then we plotted the median out of the 200 realizations and the standard errors. So the first thing that you might see here is the wider the confidence interval is for the joint model. And that could be, so if we look at the distribution of this model and the variability of the random effects, they were quite high. So that only reflects that the joint model did capture all the fluctuation of this biomarker. And we can see that within the predicted survival. Whereas in the multi-state model, we have already discretized it. So we are saving that fluctuation by the discretization that we already did. And we just got narrower confidence intervals. Right. So to sum up with the first example, we've covered how a multi-state model can be used for a clinical application and how we can how we can use it when we have a longitudinal variable and time to event outcome. We also see that there are different ways that we can think about how we define the living state. By discretizing the time-dependent biomarker, we compare two different models, and we also compare to a joint model that is quite popular. And another advantage that we would have by using a multi-state model is that we don't have to compute marginal estimates. So what happens when you have a linear mixed model is that your marginal likelihood is going to be conditional to the random effect. So you're going to have to integrate that. You don't have to do that to get population-based inference in the multi-state model. So that was the first example. I don't know if there are any questions. I might be talking a bit fast. There's a question.
Joanna tried to use more like one biomarker at the same time. For example, instead of having
No. And then, well, it depends how they're related to each other, I guess. Because, yeah, no, like the answer is no. I haven't. Right. So now I'm gonna be talking about the PLCO trial data. So this is focused on prostate cancer, and what PLCO stands for is prostate, lung, colorectal, and ovarian cancer. This was a very large randomized controlled trial that was conducted by the National Cancer Institute back in 1993. And before going again through the model and to what I've done and what I'm aiming for, I really want to spend some time describing the process and the clinical details, what we mean about screening and what we mean by natural history of prostate cancer. So first of all, what's screening? So screening is looking, well, the setup for cancer before a person has any symptoms. So if we were to see the disease progression in a timeline, we would first have the onset of the tumor. So the disease is present, but might not be, the tumor might be not large enough to be detected. There might not be symptoms. And then at some point in the future, it becomes screen detectable, meaning the cancer can be detected by a blood test, for example, by a scan, by an MRI, by a biopsy, etc. And let's say they miss to detect the cancer in this state, and then the cancer might progress to a clinical diagnosed state. And what that means is the patient already has symptoms, and that's how they go to clinic and they get diagnosed with cancer. So there's no strict or standard screening strategy for prostate cancer at the moment. So what they do is a blood test, and they look at something called the prostate-specific antigen. And based on that, they might follow up with either another test or a biopsy or MRI. And there's another screening strategy as well. They do, well, screening technique, sorry, that is the rectal examination. But apart from that, there's no standard screening strategy. So what happens? This window is very important. So how long do they spend in the screen detectable phase before they move into a clinical diagnosis? Because that's when you can actually make an intervention if that's the case. And this might vary depending on the PSA profile of the patient. So that's where we're aiming to model. So we're aiming to model or to estimate how long the patients spend in the screen detectable phase before transitioning to a clinical diagnosed phase, and how we can use the PSA value to inform how long they're going to spend. So how it affects the sojourn time, basically. So what we aim for is to model the natural progression of prostate cancer. So by natural progression, we mean there's no intervention, it's just the progression of the disease itself. And we aim to estimate the sojourn time, so how long they spend in screening detectable phase, according to the PSA test, to develop screening strategies. So where should we looking at the patient, depending on the PSA profile, or how often. So now talking more specifically about the data, the PSO trial included roughly 76,000 patients, and they were randomized into screening and control group. The screening group received an annual PSA test value, an annual PSA test for 6 years, and the men were between 55 and 74 years old, and they were followed for a median of 30 years. So there's already a model that has been fitted for this process by Rick and other authors, where basically they define what we just described. We have the first stage, that is a healthy person, a healthy individual. And then the second stage would be a screen detectable phase. The third stage would be a clinical diagnosis, and there's the competing risk of dying. So this model has already been fitted. They accounted for age varying hazards and misclassification. So basically the probability of being screen detectable when you were healthy, or the other way around. And yes, so now what I'm aiming to do is to include the PSA test. So before I can go into the model, I want to introduce what information we're observing per arm. So from the screening arm, we have the longitudinal biomarker, that's the PSA test. And then basically, what we define as screen-detected cancers are confirmed biopsy after a positive screening. So a positive screening would be you have a high PSA, then therefore get a biopsy, and then a biopsy is positive, then you're screen detected. Once it has been screen detected, then there might be a different clinical decisions. They can be surgery or anything. And basically, all this to sum up, the transition that we would observe from the screening arm would be from healthy to screen detectable, or healthy to. And for healthy to screen detectable, we're gonna have an interval sensor data, meaning we do know the exact time, we just know the interval, and we're gonna have exact transitions for moving to healthy to that. And then for the control arm, so the control arm has no intervention. They can only progress if they get symptoms. So we don't have the screening. So the transition that we would observe from the control arm would be from being healthy to clinical diagnosis or dying. So a bit of summary. From the screening group, we have interval sensor data for states 1 to 2, exact time data for state 4, that's dying. And from the control group, we have exact time data for states 3 and 4, so we know exactly where they're clinical diagnosed and where they die. And so if we see this process and we think about the way or the information that I just described we have from the screening group and the control group, we don't really have any direct information from moving from screen detectable to clinical diagnosis. So that is something when you need to fit this process in this way. Right. So if we go back to the first example and we kind of see this process, we have the same setup in the sense that we have a longitudinal biomarker, we have a PSA value, so the patients are coming every year to get this blood test, and then we have a multi-stage model of disease progression. So what we thought about is, okay, can we just borrow the same idea? Can we just discretize this biomarker, define living states, and then get different screen detectable states, and then we can account for a different sojourn time given the PSA values? That was the question, and that was what was explored. So basically, what I did is I extended the healthy state given the PSA value. So now, if we remember, this would be healthy in the original or in the first model. Then we would have screen detectable clinical diagnostic dying. So we use the PSA, we discretize it, and we extend the healthy state. And we also extend the screen detectable state. And that's because that's what we were aiming for. We want to see if there's actually a different behavior given the PSA value results. And this would have been a nice way to account for that. Because if we would model all these hazards differently, then we would have a different estimated sojourn time. And then we would say, okay, if a patient has a PSA value between this range, then they're gonna spend, let's say, 3 years in screen detectable phase. And if they have a PSA value within this second range, then they're gonna have a different sojourn time. We tried this, and it was complicated. It was complicated. I faced a lot of convergence issues because, again, we don't have direct information here. As soon as I started to relax and constrain or trying to add more layers to the model, because obviously you want to account for age, you want age varying hazards. The older or the younger the patients are, this is going to affect the survival and the way they move through the process. And yeah, didn't work. I tried exploring a simulation study, and basically we came into the conclusion that the control group was adding a lot of noise to the model. So there's many paths that the control group can have, because we only have healthy to clinical diagnosed. So that was perhaps causing problems. So we thought about a different way to go around it. That different way is a frailty model. So what a frailty model is a mixed effect models for survival. And what a frailty model tries to do is to account for unobserved heterogeneity within the patient. So what we thought is, okay, can we use the PSA value to link it in a way that we can classify the patient. We can classify the behavior of the patient within the process. So do we have patients that move faster through the process or slower? So in this plot, basically what I have is the PSA trajectories from some patients, and they're labeled given the first PSA value. So we can see there's some potential cluster behavior. Normal PSA values between 0 and 4. Something between 4 and 10 might be abnormal. Something bigger than 10 is definitely something that they want to follow up. And yeah, so what's a frailty model, or how can you specify it? A frailty model, you can specify it from a parametric perspective. So you can assume the random effects follow a normal distribution, for instance, but that would mean that usually that would mean that you need to compute the marginal likelihood, and that could be computationally expensive and infeasible if you have high dimensional setups. So another way to do it is just following a non-parametric approach. And what does that mean? So non-parametric approach, what we would do or how we would change the likelihood is basically following the likelihood I showed before. We have an individual likelihood contribution, their observed trajectory conditional to the first state, the parameter vectors and the cover rates. And then we use the law of total probability. So basically we're gonna have the joint probability of the observed trajectory times the probability of belonging to each class. And then we sum over all the classes that we've defined. Right, so the probability of belonging to each class is what we define as masses, and these masses can be computed using a logistic regression. So as a first model, I came back to the 4-state model. So just having healthy screen detectable clinical diagnosis and dying, but I added cluster-specific intercept from the transition from being healthy to screen detectable, and in a non-parametric way. So this was the results, and from this we can see that the probability of belonging to the first class is high. We have a probability of 86%, with a standard of 0.34, and we can also see that being class 1 means that you're moving slower to the next living state. So basically, it's better to be in the first class of this process, because the next living state is screen detectable. So there's disease progression. And right, so to sum up, because I'm running out of time, the aim or the next step is to link this Latin class to the longitudinal PSA test. Given the screening control format of the data, this is not a standard multi-state model. And as I mentioned before, we can face convergence issues, identifiability problems, or it can be also sensible to initial values. And yes, that's all. So thank you for your attention.
We have a bit of time for questions. I'll see if anyone online has a question, but until then, questions in the room.
Thank you very much for the talk. One question that I have is, what is the connection between the number of states and the sample size in total and in each state? What is that? Do you need a big sample size for your model?
So I think more like it could be connected, but more further than the sample size is the transitions you have within the patient. So you might have a few patients, but you see them quite often. So you might have a populated transition matrix, and that would be nice. But you can have tons of patients, but they don't really move very quickly through the process. So then you have, that's what I do. So yeah, I think perhaps the transitions that you observe are more important than the sample size. Yeah. Yeah, so I did install this advertising in different ways, but you would need to, so if you define more states, then the 4.5 is subject to the way you write this advertising. So you would have to perhaps modify that. But yeah.
What's the benefit? I think that is the benefit.
So what's the benefit of having more states or fewer states? Yeah. So I guess for this specific process and data, we could allow to discretize in this way, and we could model, and we could fit a model. And also, I don't know, I don't think there's an answer what's best. So I think obviously as you increase the stage, you increase the number of parameters, and that could be an issue as well. But for this specific setup, it performed very nicely, because then you have highly fluctuated biomarker that you have discretized. So you still account for that variation, but not in an individual level. And it worked very well. So, sorry, the original question was? what was what was that? So yeah, and for the second one, obviously we have a different setup, we have a different data, we have a different study design, and when we try to post something similar, it didn't work very well. So if we think about, and that's why I perhaps was a bit slower in that part of the study design, we didn't have direct information for some transitions. So that was a bit more complex in terms of fitting a model and efficacy problem.
All right, Alicia has some questions as well. She's saying, in the liver cirrhosis case study, first of all, is the effect of time specified using splines also in the living transitions? And if so, do the constraints across transitions apply to the spline parameters too, or just the treatment effect?
No, so these plans were only fitted for the hazard for death. There were constraints across the transition, yes. So for the forward transition, so moving forward in the process, were constrained to be the same as well as backwards. Just the treatment effect. Oh, can you just explain the second part about treatment effect?
Yeah, Alicia.
Can you hear me? Can you hear me? I'm not sure if this is working. Yeah, sorry, I can't turn on my camera here. So my question was on the models for the living transitions, right? And if I heard correctly, you said that we don't have a spline of time for these.
No.
Okay, so then the constraints are on the log linear effect of time and the log linear effect of the treatment. Is that correct?
The constraints are.
So is it on the, let's say on the gamma 3 of treatment, as well as, let's say, the alpha of the time?
No, so the constraints were within the whole hazard. So the hazard from moving forward within the process in this case were the same from 1 to 2, 2 to 3, and so on. There's time included, but there's no spline effect. And for the hazard for death, there's no constraint in the treatment.
That's fine. Yeah, you answered my question.
Okay, thank you.
Alessia, do you want to ask your second question as well?
Yeah, so the second one was on the Kaplan-Meier plots, always for the same case study. I didn't catch what the light gray curves were. I may have just missed that.
So I'm not sure if people could probably not hear that. Yeah. So that was, what are the light gray curves in the Kaplan-Meier plots?
So if we go back to the model, so that's basically the individual predicted model-based, the model-based estimated survival. So we would have the individual model-based estimated survival for all the patients. In this case, if we look at the hazards, we don't have any individual patient characteristics, so we can actually just visualize 8 curves, but in total we have 488 patients, so 488 predicted survival curves.
Okay, thank you.
All right, we have to vacate the room soon, but thank you all very much for your questions. And this is the last talk for this term. The next term will start in May. That's when the seminars will resume. But thank you very much, Ilse, for this great talk.